Section 2 is models and modeling with representing motion. So the real world mathematically is usually actually messy and complicated. Um, it's hard to actually come up with like a good clean formula for what's going on. So we simplify things. We tend to really simplify stuff down. So we ignore real world details in order to reveal patterns that occur over and over. And so we're going to be doing that in this class. And even though we're really simplifying stuff, we can still get a great idea of what's going on physically using simple mathematical equations for the things that we're going to be talking about, okay? For example, a swinging pendulum. You know what a pendulum is, right? A vibrating guitar string, a sound wave, jiggling atoms in a crystal. These are all very different things, but they all share a common characteristic. They're all examples of an oscillating system, something that's just kind of like, I could say vibrating back and forth or swinging back and forth, and they're all pretty much the same thing. So if we take a simple oscillating system like a block, which we'll call a mass, attached to a spring, and what that'll look like is we have a wall and then a spring, and we can just do this, and then the block like that. That block will be springing kind of back and forth, and that could be modeling any of the things that I just mentioned, okay? So this system right here is very basic, but it is an introduction to modeling all of these oscillating systems that we have. And it's great for that.
And what's the difference between oscillating and reciprocating?
It's the same thing.
Okay.
So what is meant by modeling? It's just taking away all of the details that mess things up and looking just at the basic idea of like the true thing that's really going on here, stripping all that other stuff away, okay? And focusing only on what matters most. The model is just a very simplified picture of reality that captures the essence of what we want to study. So what is this thing fundamentally? Oh, it's a pendulum swinging back and forth, okay? Yeah, we have drag and we have tension in the string or whatever it is, and we have all kinds of other stuff, gravity and whatnot, but fundamentally, what is it? It's a ball swinging back and forth on a string or something, okay? Fundamentally, what is it? It's a spring and a box on a frictionless plane. Okay, great, that's what we can do, okay? So this idea right here that I just drew out is something that we're gonna focus on also. Not necessarily now, but soon. All right, the particle model is something that we're going to be doing all year long. So we'll take some object, whatever it is. It could be a person, it could just be a ball, a bowling ball or something like that. It could be a vehicle, it could be anything, and we're going to turn it into a particle, okay, just like a pinpoint object. And most of the time, the reason we can do that is because the object itself is going to be modeled as something that is not influenced by its size or shape, okay? So the object as a whole is not influenced by the details. So like the size, the shape, whatever, okay? All we need to do is keep track of the motion of the single point that is represented by the object. So therefore, we consider the object as if it was just a single point. We treat the object as if all of its mass was concentrated into that single point, and it all moved together. No rotation, no twisting, no turning, nothing. It just moved all as one single point. In doing so, we're representing the entire object as a particle, and that's where the particle model comes from. So simplifying a motion diagram, like you were doing back in section 1, into the particle model. So we have the motion diagram for a car stopping. We here had to draw the car as 4 separate cars. And now you can see with my little dots here, I just simplified it into a particle model. Made it super easy, okay? So the same motion diagram using a particle model, the same amount of time elapses between each frame. We have position 1, position 0, I guess they're calling it, and then 1, 2, 3. Without drawing the car, we can see exactly what happened, okay? We understand that it's a car, like in our minds. We see the dots, we know what's going on, all right? The number shows the order in which the frames were taken. And the single dot is used to represent the object. It's a piece of cake that way. All right? By the way, what was going on here?
Slowing down.
Cars slowing down quickly or not quickly?
Pretty quickly.
Pretty quickly, yeah.
Really?
Yeah, it's like, oh, dear.
Well, he's at a normal motion that is slow. Slowly.
You actually cannot answer that question. How come?
There's
because-
no
Yeah, there's
thinking
no.
about the data thing.
Yeah, there's no model about how frequent this is taking.
We have no idea how much time is passing between each frame. And we have no idea how far apart they are.
That's what our imagination's for, though. It's like, oh look, it's a deer. We're going like 70 miles an hour.
Could
instantly
be,
slam on the
but it
brakes.
also could be over the course of
Stoplight. Something slow.
1 minute.
seconds.
This is science. Science isn't based off your imagination.
But we need to know for sure. Okay? So you cannot answer that question. All right, how about this one? The particle model for two falling objects. On the left we have a rock, on the right we have, looks like somebody diving. What do you see?
Oh, it's like that one thing that you're talking
They're
about
accelerating.
Okay, they are accelerating, they're speeding up.
at the same rate.
Okay? How do we know that?
We don't.
Because as time goes on, the gap gets larger.
As each dot from 0 to 1 to 2 to 3, the gap, this distance here, is getting farther and farther apart. So they are speeding up. Are they going super fast, slow? What's going on
We
here?
don't know.
We don't know for sure because we don't have what?
The
Data.
measurement of time.
We don't know how much time is going between each one. However, we can assume that they're not going super slow. How do we know that?
Because of how fast that gap is.
Yeah, that
Yeah,
gap,
it is.
there is a gap that's growing, right? But there was a gap to begin with. So although we could have zoomed in, I suppose, we don't know the scale. So it's tough to say really anything about how fast they're going here because we just don't know the interval. Okay? Good.
This reminds me of that bungee cord thingy story that you
Oh,
told
yeah.
us last year.
All right, so we have this one. 3 motion diagrams are shown. Which is a dust particle settling to the floor at a constant speed? Which is a ball dropping from the roof of a building? And which is a descending rocket slowing to make a soft landing on Mars?
I don't know.
You just know them all?
Yep.
Look, yeah.
A is ball.
A is the ball.
Uh-huh.
B is dust.
This one's dust. And this is the rocket.
Yep.
How do you know?
Because it says descending rocket slowly to make a.
So what should happen if we're descending to a stop?
It's like
It's accelerating
Big
to
to
slow
small.
stop.
Yeah, we should be getting, the dots should be getting closer and closer and closer, and they are here. Okay, so the rocket is right. What else?
Dust is a constant speed.
Because
Falling at a constant
The dust is
speed.
settling at a constant speed, and that's what's going on here. The gap between each one of these is the same each time. Okay,
yeah,
good?
it's because the surface area for the wind resistance is heavier than the mass of it. So it just
Uh-huh. And what about the ball? How do we know that this is the ball?
because it's called gravity. When you start to drop something, it gets faster and faster.
The ball should be speeding up as it falls, and that's what's happening here. The gap between each one of these is getting greater and greater and greater. Good, so this is correct. And like I said, a short section here, so that's it.